Lovely. How are you doing, Ellen? Lovely to see you
I'm
again.
fine. How are you?
Good, thank you. I know it's an early start, but you have to put the makeup on and everything. Is the male privilege of just looking like this. Obviously, we've spoken a few times, but I believe that some of the people who are going to be listening to this might not have even heard of Parabon before, or even what this technology is. So, with that in mind, could you tell us who you are and what it is you do, please?
I'm Dr. Ellen Graytack, and I'm the Director of Bioinformatics at Parabon Nanolabs. I've been there for 12 years. It's actually the only job I've ever had. I came straight out of my PhD, did 1 year of a postdoctoral fellowship, and came straight to Parabon. And so since then, I've been doing really the most exciting work that I can imagine. Trying to work with really, really challenging questions about what we can learn from DNA. What can we apply computer methods to understand what the DNA is telling us? And really the most interesting application that we've worked on is forensic science, working with forensic DNA samples and trying to generate new information from that DNA beyond just who that person is. Because, I mean, if you can know who that person is, that's great, but you have to have a sample to compare to. That's the traditional DNA forensics. You have the sample at the crime scene, but you need a sample to compare it to. Someone in a database, a suspect you've already identified. And if you don't have a match to any of those people, then the DNA really can't tell you anything else. And so what Parabon did was come along and ask, what else can we learn from that DNA? And the DNA is a blueprint for that person. It contains all the information that defines what they look like, as long as we can find it. And so that was the work that we started with, was, can we predict aspects of this person's physical appearance, as well as their ancestry, in order to help law enforcement know who they should and shouldn't be looking for.
Right. So when we first got in touch, I had seen in the media, instances of the Parabon snapshot being used, and with the non-scientific background, you hear about these things and it sounds like a magic bullet. It sounds kind of sort of miraculous. You mentioned physical appearance and ancestry. Could you talk perhaps a little bit about what new information you can actually glean with these techniques, and how does it work a little bit for perhaps the non-scientific mind?
We focus on externally visible traits, so things that a person is making public about themselves every day when they leave the house. So we're not looking at anything private like their health or medical conditions, anything like that. We're only looking at physical appearance, and we're focusing on those aspects of appearance that are passed down through families. So they're really highly genetic, as opposed to being influenced by the environment. So something like body weight, there is a genetic component, but has such an environmental component that it would be very, very hard to actually predict with any accuracy. But on the other hand, things like eye color, hair color, skin color, and freckling, we predict those components, and then also the shape of the face. If you're told that you look like one of your parents, well, that's because you've inherited their DNA. But of course, your DNA isn't exactly the same as theirs. And if you have a sibling, they look different from you, even though they have the same parents. And so it's by studying how people differ, physically and also genetically, and trying to find, what's common genetically between people who share the same trait. That's how we do this work. Is we start with a database of people with known appearance as well as DNA. And so we can study, what's distinct in the DNA about the people who have blue eyes versus the people who have hazel eyes or brown eyes. And so we can pick up, so what are the unique signatures of the DNA that leads to blue eyes or leads to hazel eyes? And then we can look for those signatures in that forensic DNA, in that DNA sample, to try and tell law enforcement if, the perpetrator or the unidentified remains that they found, if that DNA is consistent with that signature of blue eyes, or if it's consistent with brown eyes. And we can put a confidence on that. Here's the probability really that this person has blue eyes versus brown eyes. And that's how we encourage law enforcement to use this information is, if we can say, we have 80% confidence that this person has blue eyes. Well, that's great. But we might have 99% confidence that they don't have brown eyes. And so that is really where law enforcement starts. They have a list of possibilities. And currently, when they come to us, the only thing they know is whether the person is male or female. And now we give them a way to narrow it down. If that suspect has brown eyes, well, it's very unlikely that this DNA came from someone with brown eyes. It's not impossible. There's a 1% chance, but, that's not where you're going to start your investigation. You're going to start with the people with lighter eyes, and then you can add their hair color and their ancestry and their face shape, all of that to get to a smaller set of people to start with. And that's how this can be really, really effective. I mean, so many of the cases we work on, the detectives have absolutely no information about who they're looking for. And so we're giving them, it's just a new lead. It's a new piece of the investigation. It's not going to give them the answer. It's not going to give them a single individual, because there are going to be many, many people who match that. But the people who match those descriptions and, lived in the area of the crime or knew the victim or had access to that building or, et cetera, it's just a piece of the investigation. But it can be a really significant piece. We also work on a lot of cases where the detectives think they have a description of the person. They tell us, we're just confirming that, what we believe is correct. And we come back and say, actually, this DNA came from someone very different from the belief that you've had. And that can really help to redirect an investigation in a different direction, look back at other information and rethink it, really. And so, I mean, we call it DNA phenotyping because a phenotype is a trait. So like an eye color is a phenotype, or blue eyes is your phenotype. And so DNA phenotyping means predicting someone's phenotype from DNA. And so what we're really doing is giving them an opportunity to learn something new that they couldn't have known otherwise.
So if, let's say, a police force were to suspect, I don't know, a 5'3" Latin American man with black hair and dark eyes, your work could potentially turn around and say, actually, you need to be looking for someone of European descent with blue eyes and possibly light hair. And then, as you say, that's a new direction.
Yes, exactly. And we have worked on cases exactly like that, where the detectives are just stunned that, oh my gosh, we really thought we knew who we were looking for. And it turns out to be someone completely different. We need to rethink how we've been looking at the information that we have.
Could you talk about one or two of those cases or examples where your work has come into play like that?
Sure. Yeah. I mean, we worked on a homicide case in Louisiana where the young woman who had been murdered, she had recently been released from jail. And looking at her phone records, the detectives saw that all the people she had called since getting out of jail were Latino males. And so that was who they had been focusing their investigation on. And we analyzed some DNA from the crime scene, and it came back, this is a person of European descent with blue eyes and light brown hair. And it was just completely different from who they'd been looking for. And that was sort of an unusual case where in that case, they actually released the composite that we produced. So we do produce a composite, which is we predict the three-dimensional face shape as well as those, the skin color, hair color, eye color. And we have a forensic artist who puts those together into a composite. Mm-hmm. And so in that case, the agency released that composite, and the perpetrator, who was unknown at the time, made a phone call to his ex-wife, I believe, saying, just tell, if anybody asks, I was with you that night. And so she called in a tip, and the detectives were able to find this guy. But it just really changed how the investigation. We worked on another case. This was an interesting one. This was actually the first case, I believe, that was that we were able to help solve through DNA phenotyping. This was a double homicide in North Carolina. And so in all of these cases that we worked on, usually they're cold cases, which means they've already tested the DNA, usually of dozens of people, and excluded them. And so in this case, they had tested the DNA of people who had been in and around the house, including the boyfriend of the victim's daughter. And his DNA, they looked at its Y chromosome, and the boyfriend's Y chromosome, which you inherit from your father, was different than the Y chromosome of the crime scene sample. So based on that, they eliminated his brother and his father because they should have the same Y chromosome. And we did DNA phenotyping, and it came back as this interesting mix of ancestry that was half Latino and half European. And that was the description of the daughter's boyfriend. So they had already eliminated him, but it made them think, well, maybe we should look at his brother. We had eliminated him, but there's not a lot of people around who match that description, and we'll just get DNA and eliminate him. And they went back, and his DNA did match the crime scene. It was just, it turned out that his DNA didn't match his father. And so it turned out he had a different father that nobody knew about. And that was why, he had this different Y chromosome. But again, the DNA phenotyping, it didn't solve the case, but it gave the detectives the lead that they needed to look in the right direction.
Right. How much DNA or forensic material would you need at present at a crime scene, let's say, in order to be able to form one of those composites?
So the amount of DNA that we need has been getting smaller and smaller over time. Up until a few years ago, we needed 1 nanogram of DNA. So a nanogram is a billionth of a gram. Wow. So you can think if you took a sip of water and we then swabbed the lip of that water bottle, we would get maybe 25 nanograms of DNA, just from that little sip.
Right.
So that is plenty of DNA to do many, many different analyses with. And so we're working down at these levels that, these are DNA samples that aren't necessarily even visible. We've worked with touch DNA samples from the victim's body or from items around, but usually it's blood or semen or saliva, something like that. But these are really, really tiny amounts of DNA. And then just a few years ago, we started using some new techniques that actually came out of the ancient DNA community. So I don't know if you've heard that they have sequenced the genome of a Neanderthal, as well as actually thousands of other people who lived thousands of years ago. So if they can sequence their DNA, we really should be able to sequence the DNA of these 20, 30, 50-year-old samples. And so we sort of borrowed some techniques from that community that they had invented from ancient DNA and started applying those to these forensic samples. And now we've gone even lower, down below 1 nanogram into the picogram range.
Wow.
So the trillionth of a gram. And I think, so the lowest we've gone is about 50 picograms. And I know recently we did one with 10 picograms, but I don't want to say we can definitely do that before I confirm it. But yes, definitely down to 50 picograms, which is just unbelievable. I mean, that amount of DNA is so minuscule that it's really amazing what technology can do these days.
Yeah, it's almost unfathomably little amount of a trace that you can actually build a sort of a face from. In a case, let's say from 20-25 years ago, where let's say somebody is murdered in a home and there's blood present, and it's still there, kind of preserved, let's say, then presumably that would be more than enough to still sort of derive the snapshot, from a 25-year-old, 30-year-old blood stain.
Yes, if you can see blood, then there is a lot of DNA there.
Right.
Yeah, we work very regularly with samples that are decades old. I mean, the DNA does sort of fall apart over time, and that does make it harder to work with. But we've been working on techniques that sort of can help put it back together, either in the lab or computationally, sort of after the fact, and we're getting only little pieces of DNA instead of big pieces of DNA. But there's so much computing power these days that we can take those little pieces and figure out where they go and sort of put them together into the data that we need. And so, yeah, we've been really, really successful with really old DNA.
Great.
I actually, as sort of a proof of concept, we worked with some data that had been published from Egyptian mummies and did some phenotyping on them just to show that you can.
You can actually, wow. So I guess sort of my last question really, as you know, in the case of Japan, there's a more kind of restrictive legal framework surrounding forensic investigative techniques. If those laws were to shift tomorrow, how do you think that would change the kind of criminal investigation landscape in Japan? And I'm thinking particularly in terms of sort of like colder cases.
Yeah, it's interesting that around the world, there is a wide range of different laws surrounding what can be done. And some countries even specifically make phenotyping illegal. The concern being that the information will be used to target a specific community. And, as we argue that it's not the information that's at fault. Don't tell your detectives that they can't have information that they could have just because you're worried about them misusing it. And so, yeah, in the places where phenotyping is allowed, it can be extraordinarily powerful. And there are other techniques as well. I mean, there's also genetic genealogy and kinship testing. There's just so much more that you can do with DNA if it's allowed. There's just a lot of concern about it being misused. But I think so far, at least in the US, we've demonstrated that it is being used properly, that this information, even if you maybe don't like what the information is, it's still a fact, and it's still something that detectives are using, and they're using it responsibly to help close these cases that they maybe couldn't otherwise. And so that's really the thing, is if there's information out there that could help solve a case, shouldn't your detectives be able to have it?
Right. Well, and I imagine just from a kind of practical standpoint, law enforcement is not going to deploy these techniques to go after kids stealing bikes, right? Like you're going to use the snapshot or familial DNA on kind of significant cases which need movement after so long, right? You're not going to spend thousands of dollars on techniques just to go harass a certain community if that were going to happen, right?
Yeah, that is very true. I mean, we're really only using these techniques on violent crimes because those are the ones, and on unidentified remains, because those are the ones that, law enforcement, like you say, wants to spend thousands of dollars on. And when it comes to genetic genealogy, that is actually limited by the genetic genealogy websites to violent crimes. And so, really, this is only being used in those kinds of crimes that pretty much everyone agrees we should be able to work on.
Well, look, Ellen, I think those are my questions. Ryushi, have you got any knocking around or?
Hey, yeah, thank you so much for everything, for all those valuable insights. Really, really great to hear all your thoughts. I just have one last question, sort of just as a sort of follow-up. So I guess in a case like the Setagaya case, which I know you and Nick have talked about in the past, and he sort of touched on it just now. So in a case like this, where there was blood at the scene and left at the scene, and DNA samples are preserved by, in this case, the Tokyo police, can you see any technical reason why the snapshot technology couldn't be applied here to work towards putting together a profile of the killer?
I don't think so. I mean, as long as the blood hasn't been preserved in some unusual way that would interfere, but we haven't run into that before. I mean, there's pretty standard, we work with stuff that's literally sitting on a shelf in an evidence room for the last 40 years, and they get it out and go take it and do a DNA extraction, and we can get beautiful data out of it.
I believe as well, it's in this particular case, it's not just blood, but I think there's also saliva and hair, and I'm not sure, the chief would be able to tell you exactly what and how it was preserved, but I think it was the whole rainbow of, I think it's pretty much everything other than semen was found present at the scene, because he was there for a bunch of hours and eating, using the toilet, and fragments of his hair also left behind because his hat was left behind as well. So I think there's the whole kind of range of, and you guys would be able to not just use blood, you guys can work across all of those materials, right?
Yeah, it would just be a matter of assessing what's the best one to use. Right.
Amazing. Thank you very much.
Yeah, Ellen, thank you so much. That was brilliant.
Thank you so much, Ellen. I think we're good. Unless there's anything else you'd like to add.
Yeah, it's just with DNA phenotyping, it's really important to remember that what we're producing is a prediction, and that there's a lot we don't know about that person, and a key component is age. We cannot get that out of the DNA sequence because your DNA sequence doesn't change as you age. And so we always make a prediction assuming the person is 25, so a young adult, and at a normal body weight. We have a forensic artist who can then do age progressions, but that's an artistic thing. Our website is full of examples of all the amazing work that we've done, and you'll notice just how similar the predictions are to the actual person, but you'll also notice that they're not photographs. It's not exact. And I mean, things like how they wear their hair, do they have scars, do they have tattoos, anything that's not written in the DNA, we're really not going to be able to predict. And so everything just needs to be taken with that eye, that we're not looking for this one individual. We're looking for someone who matches this description. I mean, in the same way that you get a description from a witness and they tell you what their hair color was, what the shape of their face was, you're just using that information. It's a little different with unidentified remains when we often have a skull to work with as well. And so we can do sort of that forensic reconstruction and then add the phenotype information on top of that. Then that can be more detailed, more, you know what the person's teeth looked like, approximately how old they were, things like that. But with DNA from a crime scene, we don't know if that person was 25 or 55. At this point, we can't tell that. And so, our predictions just have to be sort of default ages. And also, everything comes with a range. We say it's most likely blue eyes, but green is possible. And so, again, like we can only put one color on that composite, but it could be lighter, it could be darker. It's probably not very different from what we predicted. But yeah, there's just, you have to sort of understand what the technology can and can't do. But when you use it appropriately, it can be very, very powerful.
So in the case of the Setagaya murders, let's say if the chief, if the TMPD have said that they believe the killer is as young as 15 on the night of the murders, and now he's going to be, let's say, 40 or in his 40s roughly, that would be something that your artist can then factor in. So if the standard is the age of 25, but we know he has to be 40-ish, that could be factored into the actual art itself.
Right.
Brilliant.
土田さん、なんか感謝の言葉をお伝えになりたいと先日おっしゃってたんで、今よかったらどうぞ。
今日はエレン先生に直接お会いできて、大変感謝申し上げます。ありがとうございました。日本はDNA 情報について、法律が制定されていない内部運用で、進められているので、DNA の遺伝子情報を十分に活用できていない。多くの殺人の現場に DNA 情報がありながら十分な活用ができていないという点で、今後、エレン先生、パラボンナノラボ社のご協力を得て、日本の事件解決について、また引き続きご指導いただければありがたいと思います。今日は本当にありがとうございました。
Great. Thank you.
Thank you so much, Ellen.
Thank you. Bye.
Thank you very much. Bye-bye.